Good afternoon from Beirut, and good morning from the US. And welcome to this talk, which is being organized jointly by the Syndicate of Computer Sciences in Lebanon and the Department of Information Technology at St. George University of Beirut. Here, I'd like to take the opportunity to welcome the Syndicate's President and Vice President. Good to have you on board. Our guest speaker today is Dr. Walid Saba. I will read a biography, quick one, and we shall proceed after that. So, Dr. Saba is a senior research scientist at the Institute of Experiential Artificial Intelligence at Northeastern University. Prior to joining the Institute in 2023, he worked at 2 Silicon Valley startups focusing on conversational AI. This work included high-level roles as the principal AI scientist for telecommunications company Astound and CTO of software company Clangu, where he helped develop a state-of-the-art digital content semantic engine called Magnet. Walid's career to date has seen him hold various positions in both the private sector and academia. His resume includes entities such as the American Institutes for Research, AT&T Bell Labs, IBM, and Congos, while he has also spent a cumulative 7 years teaching computer science at the University of Ottawa, the New Jersey Institute of Technology, the University of Windsor, which is a public research university in Ontario, Canada, and the American University of Beirut. He has published over 45 technical articles, including an award-winning paper that he presented at the German Artificial Intelligence Conference KI 2008. Walid received a BSc and an MSc in computer science from the University of Windsor, Ontario, and a PhD in computer science from Carleton University in 1999. Both of these universities are in Canada. Walid today will be sharing his insights on the topic of reverse engineering of language at scale towards symbolic and explainable large language models. So with that said, I yield the floor to you. Please go ahead. Your call.
Me?
Yes.
All right. Well, good morning, good afternoon, your time. I want to thank you, thank Dr. Marcel Karam and Dr. Wadia Jaidini, actually, for this opportunity. Let me share my screen and start. Is everybody ready?
Yeah.
All right. Can you see my screen?
Yes, we can.
All right. So can you minimize that? All right. So I will be talking about the subject of the day, large language models, the most famous of which is ChatGPT, which everybody by now knows about, including my grandmother. But I might not say what people expect these days people to say about these things. So I'm going to be a little bit off the norm here. My opinion about what's happening is probably not a very common opinion. In any case, the subject is really what happened. Where are we? What is all this hype about, or all this real news? It's not all hype. And where do we go from here, in my opinion, anyway? So let me start with saying something about the really unprecedented. I've never seen this in technology. The amount of alarming news that comes out every day that There's an existential threat. AI is going to, there's a danger of having robots smarter than us and all this talk. Including what one of the pioneers, he's not the godfather of AI, really. This actually is an example of how much media exaggerates. Jeff Hinton did his PhD 40 years after AI was established, so I don't know how he could be the grandfather. But in any case, he's a well-known, respected research scientist. He won the Turing Award, actually. And he quit Google recently and is now warning of the dangers of AI. I'm not sure what he's talking about. We'll get to that a little bit later. So when I hear about the danger of AI and AI is here, I feel like I was in a coma and I woke up and AI has arrived and I didn't know about it. It was not too long ago, less than a year, that we were afraid actually of an AI winter where AI was failing all over the place. For example, in the chatbot industry, there were tons of companies that started developing chatbots. None of them succeeded. Very few people have patience to use chatbots because they don't have any intelligence whatsoever. Actually, the failure was so huge that it was reported on as a big bubble that got burst. These chatbots were developed using the same technology of ChatGPT, more or less. And we'll get to why ChatGPT is different from these. Also, not too long ago, we realized that all this talk about autonomous driving is just that, talk. All we have is basically advanced cruise control. There's nothing called autonomous driving. And this is after billions, literally billions of dollars were spent. And again, this technology was based on the same technology that's underneath ChatGPT, which is deep learning, deep neural networks, basically. And that didn't go anywhere. So this talk of, and this was all like, whether it's in the chatbot industry or autonomous driving, this was all a year ago. And now we are afraid of AI. So, that's not quite where I'm coming from. And I think this is being overdone for whatever reason. So what's my take on what's happening with all this confusing and conflicting information? What I believe has happened, because I've been in the field since forever, actually. I lived through the first AI winter. That's how long I've been in AI. I think what we have right now is massive, massive compute power and lots of data at a scale that we never imagined. So we have, and you combine the two, and what you have is massive data analytics at a very large scale. So you can do what I like to call computational statistics. Analyze this massive amount of data, try to find some patterns and regularities, and try to generalize and extrapolate to do some predictions on new data. That's really what's happening, and with relative success. But any talk of AGI, artificial general intelligence, or machines that surpass human intelligence, this is really foolish talk. We're not even close. We don't have anything that truly understands or can reason like humans reason, or at the level of even a child. But we have very successful computational machine learning or statistical learning. That we do have. So Don't worry, don't be alarmed. Everything is okay. Now, with that background, so now you know where I'm coming from. I didn't join the party. I didn't join the hype. But I will talk about the good, the bad, and the ugly. There's a lot of good that has happened, a lot of progress. So my talk will be structured like this. I will briefly say what happened really, and how did it happen. I mean, something did happen. We're not where we were a couple of years ago. Obviously, something has happened. I will discuss what I think did happen. Essentially, my focus is on large language models, which is now synonymous with ChatGPT, if you want. But then I will discuss the issues with these large language models, things like what they call hallucinations. That there's we don't have machines that can do hallucinations because that requires really intelligent beings, but they call it hallucinations, which is statistical malfunction, if you want. The issue of explainability, I'll discuss that briefly. I published something on that. And truthfulness, the ground truth. Can these systems check facts? And then I'll briefly get into how did we get here? Why did these things succeed more, at least, than decades of work in symbolic natural language processing? By symbolic here, I mean rule-based, logic-based, logical semantics, in the tradition of Chomsky or Richard Montague and others. Why did that work fail, while large language models at least achieved a lot more than these approaches? And then I'm going to say maybe the reason they succeeded or they went further than the old traditional methods is not because of the paradigm, but because of something else. And that tells me, wait a minute, maybe we can get the best of both worlds. Something good has been achieved by large language models. What is it? If we can take that good and add it to the good of symbolic methods that are explainable, they don't hallucinate, they can have access to the ground truth because they are truth verification systems, then we get the best of both worlds. And then we might have really scary AI. So that's where I'm coming from. And then I'll welcome any questions you might have. By the way, even throughout, if you need to ask, by all means. Okay, so let me start with what did happen in AI, really? I mean, what is all, or if you want, what is all this noise about? What's happening? Well, in short, so-called large language models have really crossed a threshold of scale that made them, that made a leap, a qualitative leap in the capabilities of these systems. I mean, just 6 months ago, GPT 3.5, there's an episode that I was invited to appear in. It's on YouTube, where we were testing GPT-3, and it was funny. I mean, it never worked. I mean, that was just 6 months ago. So the scale that we went to really resulted in a qualitative improvement, not just quantitative. Something different happened in the last 4 or 5 months. So that's what happened. That's what all the noise is about. Now, how did it happen? Well, the keywords here are bottom up is a keyword. I'll get to that later. Reverse engineering is a keyword or a key phrase. And at scale. So these are all key key phrases that made this thing, that made us get to the point where we are at. Really, there was a massive bottom-up reverse engineering of language at scale. Let me explain what I mean. The latest numbers we have, of course, nobody has the actual numbers, but the reported numbers, is that GPT-4 was trained on more than 300 billion words. Now that's the equivalent roughly of 4 million books, if you can imagine. And that's roughly, according to psycholinguistic data, that's roughly equal to the number of words that 40 people will hear in their entire lifetime if they lived until the age of 80. Now just imagine, 40 people living 80 years will not hear so many words as ChatGPT. But we know children don't learn language this way. I mean, if they had to learn language this way, a child will have to be 3,200 years old before they can speak. Obviously, that's not how we learn language. Now, again, continuing with how did it happen? There was a breakthrough a bit more than a year ago. Actually, it's almost now 2 years ago. There's a classic paper called Attention is All You Need. And what these guys developed, of course, GPT-4 now has advanced this technique, but essentially this is where the whole thing started. And really, what is this all about? These models were encoding words you probably all heard of: birth and transformers, and previously glove and word2vec, and all these vector-based semantics, word embeddings, we call them. Now, these approaches were encoding words and slightly surrounding context. A new model was developed, which is brilliant, actually. It was very smart, that said, wait a minute, when I'm training my system, I want to train it on the words, the word embeddings, but I want to take the position of the word into consideration, because syntactically, not everything goes with everything, you know. So there's an order to the words we use in a sentence. Quantifiers are used before a noun phrase. Prepositions are used before a prepositional phrase. So there's some. They were trying to encode the grammar by encoding the position of the word, which was brilliant, really. And that took everything into another level, because now we're encoding the syntactic structure in a way in the embeddings, in our vectors. So brilliant idea. And then they created what they call an attention window. That's why the title of the paper is Attention is All You Need. Essentially, they were saying, let's pay attention to the context when we are encoding and training these networks. Now, on the extreme right, where you have that spherical, fully connected graph, if you have a sentence like the firm for which Jacob worked sent him to New York. Now, you would like to encode all the combinations structurally and all their positions. But this is a very, very expensive process, because with every word you encode, you're raising you're increasing the complexity by a factor of 4, which becomes like polynomial degree 4, and that can be really large, because these things are trained on billions of words. So you can imagine quadrupling is huge. So what they said, okay, we can't do all combinations. I mean, it's like chasing infinity. There are many ways of doing this, but not fully connected. You can do it random. So you can pick some random set of words and encode their position. You can do a running window if you want, like a linear, which is graph B. So basically, let's say 10 words before, 10 words after, and this is a running window, keeps the window keeps shifting as you go forward. Or you can do global attention, like basically global context if you want. And you can do a combination, which they call Big Bird. Essentially, the bottom line here, without the technical details, is They widened the context and they encoded the position. So now you have a syntactic structure that is 32,000 words wide. So you are learning really all kinds of combinations of how we might talk. That's massive. That's huge. And that requires a lot of compute power, as we all know. By the way, training GPT-4 costs $10 million. Every every round of training costs $10 million. So this is not for everybody. Okay, so that's what happened. And the network itself is massive. I mean, 1 trillion parameters. A parameter here is either the red arrow or the little red circle. Basically, a parameter is a weight. Neurons get inputs from massive numbers of neurons, and every neuron, as it goes in, has a weight. That's what the parameter is. So we have 1 trillion weights in the network. That's huge. And that size allowed it to really discover the patterns with the large attention window. It allowed it to discover the proper way of speaking, let's call it. Okay, but they didn't know that they're learning more than they thought. What do I mean? They were after learning the syntax and how to speak properly. But when we, in our linguistic communication, all these books and all these web pages and all these, any content, any linguistic communication that's a human creation, indirectly encoded in it is our semantics and our common sense knowledge. When we talk and or write, when we speak and write content, indirectly we are encoding common sense knowledge, because we don't say everything when we are writing. We assume the reader will pick up the rest. So indirectly, we're encoding in our language, not just syntax, we're encoding semantics, and we're encoding some common sense or background knowledge. So at this scale, these systems not only figured out how to speak properly, which means they didn't just pick up the syntax, they picked up a lot of semantics and a lot of common sense knowledge. So this is what happened and how it happened. Now, of course, language is infinite. We know any language, all languages, actually even formal languages like Python. The number of valid Python programs that your Python compiler is ready for is how much? Infinite. It has to be ready for any valid Python program. And any here is infinity, right? A Python compiler will not say, sorry, although this is a valid Python program, I can't execute it. No. So even formal languages are infinite. And English and natural languages, English is one of them, but any natural language is a recursive set, is an infinite set. So it's this white area, if you want, and it's unbounded, it's infinite. Now, large language models approximated that infinity at a very, very massive scale. But the genius in these models is what they did is they learned a distribution that covers syntax, and now they can generate. What do I mean by generate? There's nothing novel in generating. They're not generating something as in the sense of creativity, the way humans have. But what they did is they learned the distribution, and now you can go and it's like you're doing a Monte Carlo simulation. When you know the distribution, you can go and now create new instances by sampling from that distribution. Bottom line is they learned how language works, and now they can put things together in some combination that looks novel or creative because they are picking things from the right distribution. So they're picking correct things and stitching together things they've memorized, but in a very novel and creative way. Not bad, very impressive. By the way, the real impressive thing here that I didn't get to is the software engineering side of things. I mean, these are massive, massive systems, and the parallelization that goes into them. And so there's besides the techniques and the novel models like attention models and transformers, there's also the software engineering story, which is also amazing. Okay, so all this stuff allowed these models to complete. They call it complete by. I'll explain what I mean. So let's say I give it when I'm on the beach. Try this actually, and you'll see how it does. You can tell it when I'm on the beach. I must 3 dots and ask it to continue. What it does is it because of all the combinations it saw in the training phase, it can come up with a word that is most likely a good word to continue with. Okay. Now, the phrase is when I'm on the beach, I must wear, is again fed back, and it's asked, give me now the next word after where, given this new context, right? So now it says, after this, my is a good word to continue with, and so on. Where my, and then it says my sunglasses is a good word to continue with. So it keeps feeding the context so far and says, okay, what's next that I could continue with? As you can imagine, if you scale this, you give it any content and it will continue because it can discover what is the best continuation given this context. They call it the prompt. Yeah, by the way, it's the next word they pick is not only it's not always the word with the highest probability. Because they wanted to simulate some sort of a creativity, and I'm not repeating myself, they injected some randomness. So what they do is when they compute the next probabilities, let's say you come up with 4 words that all are highly probable as good continuation. They don't always pick the one with the maximum, absolute maximum. Sometimes they pick the next best. And this randomness makes it look like it's creative and it's generating original stuff. Nice trick, very smart. Okay. Now we call them large language models, but are they models of language? Large language models are not really models of language. They are statistical models of the regularities you find in massive linguistic patterns. So it's not exactly correct to call them large language models. They are more statistical models of the regularities they find in linguistic communication. And why is this important? Models usually explain a phenomenon, like force is mass times acceleration. That's a model, right? We have a phenomena, and the model here that we discovered is that force is always mass times acceleration. That's a model. Models are explainable, and they explain a certain phenomenon. But explainability requires, and I'll describe what I mean by invertible compositionality. Basically, explainability is inference in reverse. If I make an inference or a prediction, or I make a decision, and someone asks me, can you explain your inference or your decision? I have to make inference now in reverse, sort of like backtrack and explain my steps. How did I get here to make this decision? So explainability requires invertible compositionality, meaning I have to be able to Because every time you make a decision, you're composing different factors, parameters, variables, and one compositional function at the end that gives you the final decision. If I have to explain where I got here, my compositionality has to be reversible or invertible. But to do that, you need structured semantics. I need to have somewhere stored the components that contributed to my decision. I'll explain shortly what I mean by that. But the point here is neural networks, deep or shallow, or any topology, any neural network cannot represent compositionality. So they can never be explainable. I've written about this actually, and this is a hot topic now, explainability in AI. The bottom line here is whatever knowledge these large language models have acquired with their massive training on a huge corpora, whatever knowledge they have learned will always be buried in billions of now 1 trillion parameters or weights or micro features. But none of these features is meaningful on its own. Remember, in neural networks, what we call a parameter or a feature is not parameters or features that we have in symbolic systems where I have an attribute, a symbolic attribute that means something, right? These systems are sub-symbolic. In other words, your typical attribute in, say, object-oriented systems or in relational databases, what we call an attribute there is a structured value that on its own, it means something, like the name of a person or the age of someone. That's an attribute in symbolic systems. In these systems, the age will be stored in 200,000 weights across the network. It's distributed, okay? And that's why we call them sub-symbolic. We don't have symbols, we have sub-symbols. But none of these sub-symbols means anything on its own. It's just a weight, 0.34, and has no semantics, has no meaning. I'll explain that further even. But so these models are not explainable. The knowledge that these large language models have acquired by processing vast amounts of text is buried in hundreds of billions of sub-symbolic features, but none of it is meaningful on its own, right? And that's why now we have a problem in explainable AI, because the network makes a decision, nobody can explain why. All we can do is look at the data and try different data set, but you cannot go inside the black box, which is really, it's really dark in there. It's a real black box because of the cognitive architecture of these systems, because of the paradigm itself. Okay, so just a little bit about explainability, although it's not the main topic here, but in a way it's related, because that's why we would like to copy what these guys did, but in a symbolic setting, so that we build explainable systems. Okay, so what is explainability? Like I said, it's inverse, it's inferring in reverse, basically backtracking our steps to explain our decision-making process. So let me give you a small example why these models cannot ever be explainable. And I underline ever. It's not about maybe we can do it next year or in 5 years. And this was proven a long time ago, by the way, in a classic paper by Fodor and Piloshin in 1988. Here's the point, and it's amazing if you're interested in semantics, and this combines everything in computer science, this notion, this concept of explainability. So here's one neuron, but okay, you can multiply that by 1 trillion, doesn't matter, same logic applies. There's one neuron and 3 inputs, and every input, like I said above, has a weight when it comes in. And we do a weighted sum, and then the weighted sum is passed through some activation function like ReLU, and then an output comes out. But without all the details, let's say 3 inputs resulted in 12, okay? And actually, in neural networks, the result will be a vector, but 12 is a vector. It's a scalar vector. It doesn't matter. I mean, it could be one number, and it could be a vector of numbers, but the same concept applies. So let's say the output is 12. Now, how did we get, if I want to explain, so someone's now going to ask me, how did you get 12? Guess what? I can't tell them. The number of decompositions of a scalar or a vector, once you compose it, is infinite, meaning undecidable. Did I get 12 by multiplying 2 by 5 plus 1? Or did I get 12 by adding 2 plus 2 and then multiplying it by 3, etc., etc., etc.? You can imagine there are infinite number of ways I can get 12. Now, if you extrapolate this to a neural network, vectors also, which are tensors, I mean, 12 is a tensor also, but it's a scalar tensor, dimension 0, okay? If you compose vectors into a vector, and that's what happens in every layer in the network as you go forward, feed forward, once you do the composition, the decomposition is undecidable because the number of ways I can decompose a vector into its components is undecidable. I hope we got this point because this is crucial. So the compositionality in neural network is not reversible. Once you compose the weighted sum and you pass it through an activation function, that's it. You're done. You cannot go back and say how you got here. Why? Because you lost the structure. You don't save the structure in these systems. There are no symbolic structures. There are no variables. There are no evaluation trees. You know how we evaluate expressions in abstract syntax trees. All the stuff doesn't exist. All you have are weights, and we're composing vectors into the next layer and pushing the output forward until we have an output. But you cannot go back and explain how you got to any level, including the final output. Bottom line, to make long story short, these models are not explainable. And that's a big problem. Actually, I've written, it's not like an official peer-reviewed paper, but it's on the blog of the ACM. And I give credit to where this started, like I said, in 1988. And still, it's nobody answered that. They ignored it, but then nobody answered it. And I give an example, a real example, where the final output after you do the weighted sum and you pass it through a ReLU function like F here. Let's say the output is 0.87, but I can get 0.87 given the variables and their weights in an infinite number of ways. So I can never go back and say how I got 0.87. Okay, I think we said enough about that. So these systems are not explainable because I cannot reverse my decision process and explain how I got here. Okay, there are other issues with these large language models. Okay, explainability is one of them, but this is not due to large language models. This is due to the paradigm itself, to neural networks, deep or not deep. But another serious problem these models have is truthfulness or the ground truth. Remember, these systems ingest massive amount of text. But while they're reading this text, they cannot verify if this phrase is true or this sentence is a fact or this is not factual. There's no access to the ground truth. There's no truthfulness verification. There's, in the old days of AI, we used to have a subfield of AI called TMS, Truth Maintenance Systems. There's none of that in these systems. They cannot, text is text. They don't know which is true, which is not true, okay, which is a problem. There's a problem now known as hallucination, but it's really not hallucination. Only intelligent beings hallucinate. I mean, even animals don't hallucinate. You have to be smart to hallucinate. It's like you have to be smart to commit suicide. Dogs don't commit suicide. There are certain things that are bad our brain produces, but only smart brains can produce, which is really funny. But so these systems don't really hallucinate. You have to be smart to hallucinate. What they do is, because they're approximating semantics statistically, statistics are just numbers, and sometimes you get funny numbers and the wrong thing comes out. So that we're calling this hallucination, but it is a bad phenomenon. But I don't like the name so much because it implies that these are really smart things, and sometimes they hallucinate. No, they're not. Okay, and another big problem with these systems is that they have bias. They sometimes produce toxic language. Actually, we're working now, a research group. We're applying for an NSF grant, really to intercept these systems because and detect toxicity like toxic language or angry language or racist language or racial bias or gender bias, etc. Now, these systems will always be susceptible to this. Why? Because they're under the mercy of their training data. And if they want to ingest everything under the sun, you will have biased language and toxic language. And so it's embedded in their training data. They will always have that. Okay, it's important to note that these things, explainability, no access to the ground truth, what we call hallucination, and bias and toxic language, keep in mind, these are not things we can fix with by scale, with more data. These are problems that are associated with the paradigm itself, regardless of the size of the data. Okay, and this is important to note. As you will see now, they are even things that are being acknowledged by the developers of these models. So that's what happened. Basically, the bottom line is few smart ideas like the attention model, the transformer, the attention window, and the rest was just sheer scale. That's all that happened. Massive, massive scale, both in compute power and the data being ingested. That really is what happened. Trust me. And actually, just a week ago, a leaked document came out of Google, and there's an interchange. I don't want to go through the whole thing. It's online, actually, and they admit we have no moat, meaning no defense. And neither does OpenAI, which are now the two top in large language models. Basically, they're saying we have no secret sauce. That's all we did. Massive scale and lots of data and trained this thing. And hey, we have something that is scaring people. That's all we have. So they're admitting what I'm telling you now. And when I say trust me, that's it. That's all that happened. Okay. Unfortunately, I would have liked to see real innovation in AI, but no. And there was a recent paper that also came out of Stanford, again, very recently, it's not even 2 weeks old, that goes through, because there were many claims made in few papers that, hey, with scale, we are seeing emergent abilities, like something is coming out that we never expected when we scale with more data. And this paper goes through all of these and says, these guys created data set benchmarks that suits their conclusion, basically, like create your own test data and claim that your test data worked. Wow, nice. Okay, I can always create my own test and claim that I did well on my own test. I wish in college we were allowed to test ourselves. No, so they proved that, hey guys, what you're reporting is a mirage, is actually fake, okay? There are no emergent abilities. You are creating your own benchmarks and then reporting that you're doing well on your own benchmarks. That's a nice game, but no, thank you. And finally, the CEO of OpenAI, the ChatGPT developer, admitted, I think this was like also a couple of weeks ago. These days, couple of weeks is like a century in technology. In a couple of weeks, developments are happening very, very fast, exponential rate almost. And he said that any new development is not going to come from here on from bigger and bigger models. Basically, I think, I'm not sure what's behind this, but I think obviously he's relying on his engineers and scientists, and probably we have reached the optimum point of scaling. In other words, things might start to dip, accuracy might start to dip down from here on, because there's a point at which you start to have diminishing returns, if not negative return, not just diminishing, because probably at some level of scaling, all probabilities become equally likely and it start to go wild. So probably the scaling, the qualitative improvement with scale has reached a plateau. I mean, we also had, I wanted to put the graph, there was a beautiful graph that shows improvement in accuracy on one axis versus the increase in scale. And the function was logarithmic. In other words, there was an increase, but very small increase in accuracy with exponential increase in compute power and data. And apparently that logarithmic function plateaued. Like now there's not even any, not just small, but no noticeable increase if we keep enlarging this. So in other words, that's the end of the line for this story. Massive amount of data. Okay, we did that. That's the best I can learn, probably. At least that's what I believe. Okay, I don't want to go through these. With everything I said about these models, well, these are, I have to admit, these are not easy tests. I make them because I know how these systems work, so I'm making them to make them fail. But if you want to go through them, I'll leave the presentation after with Dr. Marcel, and he can make it available for you. But there are nice examples that I'm here testing different phenomena in language, like intentionality, reference resolution, basically deep semantic understanding. Like here's one, number 9. I'm asking it, what does she refer to here? And the sentence I'm giving it is, since she's always there, Anne asked Mary what time the library closes. And it says it's ambiguous, but it shouldn't be ambiguous. If you say that to anybody, they say, oh, since she's always there, Anne asked Mary, meaning Mary is always there. That's why I asked her, because she knows. She's always there. She knows when the library closes. Common sense. Anyway, and by the way, if you try these, because of the statistical nature of these systems, and remember the randomness added, you might try the same query. Actually, I try them sometimes again, same, and I get a different answer. So these are unpredictable, random outputs. So you might not get the same output I'm showing here. But regardless, this is not a good way to test ChatGPT. Okay, right now, most people are testing it by using it as an information retrieval system. And they will do okay here. That's really what they're good at, actually. You give me content, I give you relevant, I continue, remember the continuation story. I can give you content that is a good continuation for your prompt or your query, because I'm good at predicting what is the most likely continuation. And it has to be also textually similar. Coherence is important here. And they're good at textual similarity, cosine of vectors, blah, blah, blah. So this is you're fighting on their playing field here, if you want, like you're playing their game. That's what they're good at. The real test, and I'll explain that now. I'm actually writing a paper now with thorough tests on an actual database. The real test is to issue queries against the database, because these systems, you can give them tables and then say, okay, here are 3-4 tables, and start asking questions against the tables. A real test would be to issue queries against a database. Could be a very small, like a couple of tables, 3-4 tables, whatever. Why this is a good test? Because here you have 0 degrees of freedom. The understanding has to be true understanding, not I'll get you relevant stuff, semantically similar. Okay, that's search, right? No, I want to play a different game. Do you really understand my query? Because we know when we make, let's say, against a database, a SQL query or a knowledge graph, Sparkle, whatever query, formal query. And by formal, I mean any change in the query will result in a different answer, right? So if you don't get my English question exactly right, you didn't understand it, quote unquote, you're going to generate a wrong query, which means you're going to give me the wrong answer. So this is a real test. That's how you should test these systems. Did they really understand my question? Now, why is that the real test? Because unlike retrieving relevant content, here to understand the question properly and formulate a formal query in SQL with the right quantifier scope, with the right logical expression, you really have to do good at everything, 0 degrees of freedom. You don't have, they cannot make one mistake in the understanding. So you have to do the right quantifier scope resolution. You have to understand nominal compounds properly. You have to attach prepositional phrases in the right place, etc. I'll give you an example. And this is an actual test I did actually. And I didn't complicate things yet, although I'm starting to work on a more thorough test. Again, like I want to report this in a paper. But here I gave it one table. Imagine one table, no complicated joins and complicated semantic relations across tables, just one table. And I asked a question like, is there an agent that sold to some client in every country? Basically, I'm saying, do we have a sales agent that has sold to at least one client, but in every country? Like they have clients in every country, basically. Even, remember, this is difficult, and this is it's not difficult for a human, but this is a real test because they cannot get anything wrong. For example, an agent here is any agent. Now, logically, an agent is there exists an agent, but really, the real meaning here of is there an agent? Is there any agent? And now it's all of a sudden for all, right? Same with some client. I'm asking not for some specific client, for any client. So again, it's for all. And this is, this goes under the challenge called quantifier scoping. But a bigger problem, I'm saying sold to some client in every country. You cannot have a client in every country, right? Physically, it cannot happen. Now, the real interpretation here is in every country, some client. So the system has to know that the scoping here must be reversed. So it's like saying, is there an agent that sold in every country to some client? That's the real meaning, right? Otherwise, it doesn't make sense. The point here is that this type of understanding tests if they really understand, because now to do all the resolution and not make any mistake and generate the right query, you have to understand, you have to employ common sense reasoning, and you have to employ all kinds of disambiguation. I hope that sends it, because, and so like I said, I'm writing a paper on this, and I'm going to have like a non-trivial database. But so far, I don't want to say I was surprised. I'm confirming what I know, because I know how these systems work. They almost failed on every query. Literally, I mean every query. So I will advise Jeff Hinton to sleep well. We don't have AI yet. All right. But I've been bashing large language models for the last few minutes. Still, something big has happened. I believe something non-trivial has happened. On the other side, I debate people that trivialize this. No, this is not trivial. What has happened is huge. But what exactly did happen that we should appreciate? And why large language models came this far, even if they're not there, but they came very far, when decades of work in traditional linguistics and like in the tradition of Chomsky, syntactic structures, generative linguistics, or model theoretic lambda calculus, logical semantics of Montague, or decades of work on formal ontology by like Doug Lennett and company and on the Psych project. And so why did all that fail? Here's my thesis. Okay, generally speaking, there are two approaches in science for any scientific explanation or any problem we're investigating. We can approach the problem bottom up or top down. Just to give you an appreciation of what I mean here, can you imagine trying to come up with, like before we had merge sort or quick sort, can you imagine trying to do these bottom up, to try to infer them bottom up from data? It's undecidable. I mean, where do you start? So in those problems, it was top down, right? You start with some known axioms about sets and their properties and collections, et cetera, and you start deducing, really using deduction in a top-down fashion. There's no way we can come up automatically by bottom up with a new sorting algorithm. So some problems are suitable for top-down methods. Some are suitable more for bottom-up. This is a well-known thing in science. Now, the issue with top-down is it's very direct, very efficient, goes right to the problem, but there's a catch. To do top-down, you need to have well-known, established general principles that you can start from, some axioms, some well-known properties that you need something to start with, right? Bottom up, you don't. You just look at the data and start inferring from the data something. So top-down has a lot of advantages, but there's a catch for top-down. Like I said, you need to have a neat theory, small neat theory, or a set of axioms that you can start from. Now, in language, we have none of that. We don't know anything about language. And when I say language, I mean internally. The language of thought, if you want, how we think and how we externalize our thoughts in language. It's a black box. We have nothing to go by. And that's why those top-down approaches didn't work, because they were playing God. Everybody made their own assumptions and everybody made their own axioms about the mind and went forward in a top-down fashion. That doesn't work. So language is a suitable problem to be approached bottom-up. Basically, these guys said, let's look at language and see what we can figure out, which is the right thing. I don't think they were doing that with what I said in mind, but it just happened that the paradigm they have is suitable for that approach. It's an empirical approach. It's data-driven. And that's why it worked, because language, we don't know anything that we can go by to do it top-down. So in my mind, that's my thesis, why they did better than top-down approaches. Now, so where do we stand now? Here's what we know. We know, and these large language models have proved that a bottom-up reverse engineering of language at scale is a viable approach. At least we know now that this is one way to discover something about language. The top-down approach doesn't work, again, because we have nothing to go by in a top-down approach. That's what we know, or that's what we should conclude, really, from this massive experiment called large language models. But like the problems I mentioned, they cannot get at the ground truth. They hallucinate. They are not explainable, and that's huge. They cannot explain their decision process. So to avoid all these problems, okay, let's take what they did well and do it in a symbolic setting. So in a sense, let's do bottom-up reverse engineering of language at scale, but symbolically. And the good news is, this is not new. I mean, it can be traced back to Frege, who said, I'll show you the quote below. And it was subsequently done by Fred Sommers, who suggested how we can uncover the tree of language, he called it, or the language tree. Jerry Hobbs, I'll show you the quote that he said. And with all humility by yours truly, and back in 2007, I'll show you the quote in the paper. And I suggested how it could be done even. So what do we mean by symbolic reverse engineering of language? We all know now, if you're doing machine learning, especially NLP type of machine learning, those guys, they love this phrase. You shall know a word by the company it keeps, because all the embedding approach in vector semantics are based on finding co-occurrence correlations between words in the corpus. So they love this phrase. Well, I love it too, but who said the word, the company a word keeps, should be measured by co-occurrence? Actually, when I test things like BERT and GLOVE and Word2Vec and all the new transformers, if you do k-means clustering, well, if you just look at the vector of a word and see its neighbors, k nearest neighbors, if you want, some 100 neighbors, you'll discover that the meaning now in vectors, even the state of the art, is accidental. I mean, you will see relations between words. They're considered good similarity matching semantically, but only because of accidental co-occurrence in the corpus. That's not where the meanings are not accidental, and they're not temporal. They don't change their meanings when we change the corpus. So that code is correct. You should know the word by the company it keeps, and I'll show you the correct interpretation of it shortly. But the company it keeps is not co-occurrence. Co-occurrence is very, like I said, very accidental and very temporal. And again, this is not new. Frege, Gottlob Frege, the logician, actually probably one of the most influential logicians, he introduced quantifiers, which means variables, and so it had implications even on programming languages. The scope of a variable, we call it in programs. But he introduced quantification, how you can generalize and make statements about universal quantification and using universal quantification. And the idea of a scope, when you introduce a variable, throughout it has a scope where everywhere it appears in this scope, this variable refers to this, and so on. So he made a brilliant, because before that we had propositional logic or Boolean algebra. He is the father of modern logic, if you want. And he said years ago, I mean, this is more than a century, he said, the real meaning of a word, you cannot in isolation talk about the meaning of a word. The real meaning of a word is all the ways it appears in all the sentences where it can appear. Now, we'll see what that means. But so this is not a new idea. And I keep telling people, stop putting this code. I mean, there are much older. This is not a new idea. Fred Sommers.
So Walid, sorry,
Yeah.
I don't mean to interrupt, but I have a few questions from our students that
Sure.
that might give you a bit of a breather. So
Sure.
I have Judy, who asks, considering that the large language models have the capacity to gather all the information already found, I suppose she says, don't you think they present a danger on the career of researcher, or supposedly danger to the career of researchers? That's her question.
I'm not sure I understand her point, because
So let me read it again. So she says, considering that large language models have the capacity to gather all the information already supposedly, don't you think they present a danger to the career of researchers?
okay, let me see, double check. Let me see if I understand it, so I'm going to phrase it my way. Is the idea here that because these large language models are reading everything, including research, right, they will not leave much room for researchers to be creative and develop new things? Is that the idea?
Yes, she says yes.
Okay.
She confirms.
Okay. So no, when we innovate, we don't reproduce stuff that was done before. We do what Isaac Newton said, we stand on the shoulders of giants when we get here. I'm mentioning some of them now, Fred Sommers, Frege, but we add our twist, which could be just 1%. And that's what innovation, that's how innovation occurs. 99% of your stuff is old stuff that goes back to Plato and before, even to Babylon, right? And we stand on the shoulders of all these giants. That's fine. But then we add our 0.1. And sometimes that's all you need. So no, there's no, because otherwise this is the end of science. Are we saying that everything that is innovative has been created already and ChatGPT can access it? No. So I will say, don't worry, keep doing research. No.
Okay,
I don't know
so
if I answered the question, but I think that's what you meant.
she's satisfied with the answer. I have a second question here. This is from Tonya. She says, due to the limited explainability of the large language models, do you think their implementation in the medical field, specifically personalized treatment, this question obviously is coming from a pre-med student, might actually be as beneficial as having a physician do the job?
Actually, because of the problem of explainability in critical places like medicine, and there are others like security or in like now people are employing this in approving applications for something. There's a danger in accepting what they give you without any double checking. Now, they can still be useful, but someone has to, so they can save time by doing this quickly and repeatedly, but someone has to edit if you want and go over, because you can't blindly take their decision, especially in critical domains. Good question. Because the explainability problem is a huge problem, especially in critical domains like medicine or, like I said, security, or if I'm trying to approve some application, I might really be unfair to someone by rejecting it without explaining why. So good point. But we can still use them, but there must be a post-checking of the output to make sure that nothing funny is happening by an expert.
Okay, so can we take more questions, or do you want to continue?
No, that's fine. That's fine, because
Okay.
we're really starting a new thread if you want. So
Okay, so so now I just received two questions. One, how, in your opinion, OpenAI could make ChatGPT more accurate, less random, and reduce errors?
how? Sorry.
So basically, in your opinion, how do you think OpenAI could make ChatGPT more accurate, less random, and would reduces errors?
Like I said, and that's why I put it in my slides. The issue, these four issues that I counted, there are many issues that they solve because they are a function of scale. But these four issues that I mentioned are really not a function of scale. They are a function of the paradigm itself. They are a function of deep neural networks, not so much of ChatGPT, right? They are a function of the paradigm itself. Explainability is a problem because in neural networks, you cannot reverse compositionality and thus trace back your decision process. That's a paradigm problem, not a scale problem. Truthfulness. If I'm ingesting text and I'm not doing logical reasoning and fact checking, I cannot decide on the truthfulness of something. So I will give you something even though it's not factual. The third one, all these are not a function of scale. They are a function of the paradigm itself.
So if you
can ChatGPT do something about it? The suggestions that have been raised by many people is hybrid systems. Make ChatGPT consult some symbolic system to fact check things before it gives you an answer.
So the sub-symbolic sphere that you mentioned at the beginning of your talk, if you when you look at that and you try to basically estimate the randomization factor, could that be a step closer to figure out how to reverse and find out why a specific answer essentially came out the way it did?
Okay, the short answer is no, but that's very short and unfair. But let me tell you why no. You see, the issue here is these systems are really a different model altogether. They are sub-symbolic. In other words, the knowledge and the reasoning and the semantics in the network is distributed across millions of weights. So imagine this. You have the age of someone. Like I want to make it. I want to explain my decision why I rejected your loan application, right? So my reasoning could be your income, the combination of your income and age, maybe, or number of employment. I don't know what factors they use, but let's say, but these are attributes in the symbolic word. You have income and it has a value, right? Age has a value. What else did we say? Years of employment is an integer, right? I've been employed for 10 years, whatever. So in symbolic systems, I have discrete, actual, standalone attributes that have values, right? The equivalence of this in these models is age will be distributed sub-symbolically by numbers that are float numbers, real numbers, 0 and 1, in maybe 10,000 places.
But
The
with,
one attribute.
but with no reference to so it's not bidirectional. It's only one directional.
Yeah, it's feed forward.
Transformation.
Feed forward. Yeah, but the issue is really the distributed aspect of it. I mean, neural networks were always called in the industry, in the field, sub-symbolic systems. And to stress the point that there are no symbols. You're not computing over symbols in these systems. There are weights. And like I said, the age attribute and its value could be in 100,000 neurons, all collectively. Somehow they represent the age. So you cannot pinpoint and go to inside the network and say, this is what happened because your age was not the right age. You can't point at age in these systems. There is no attribute called age. Okay, so they are sub-symbolic. They don't have symbols that mean anything.
Fair enough.
Now that has an advantage, but it has a disadvantage that they cannot be explainable at all. Now what they do is they try to explain the decision by investigating the data. They say, it looks like this inference was made because your data is so and so, but you can't explain the logic inside.
So it's an ad hoc, basically, explanation, really.
Well, it's just the way that I find patterns in the data that are meaningful to me, but don't tell me how I got here, in a way. I explain this in, like I said, I have the title. It's a short post on the ACM blog. And I really explain why you cannot do inference in reverse in these models. And that's why explainability is a big problem.
Great, thank you so much. So another one. Okay, so this is from Rami. He says, as per what you've explained to us today, 6 months ago, AI was still dumb. And now it has basically scary amounts of data in its database. Will we be experiencing something like the rise of the machines anytime in the future, and how dangerous could that be? Good one, Rami.
No, like I said in my first slide, actually a couple of slides at the top, sleep well, all is okay. We don't have intelligent machines yet to be scared of them. But here there's a philosophical issue I want to mention. Even if we have super intelligent machines, nothing can, and this is said by the renowned philosopher Dan Dennett. He said, which is brilliant, he said, what are people afraid of? To be dangerous, you have to be conscious, right? Not just intelligent. Intelligence alone doesn't mean dangerous. To to be danger, you have to be consciously making a decision to be dangerous, right? And machines will never be conscious. So all this talk about dangerous machines is talk by people that love sci-fi movies. Now they can be dangerous in that they can produce bad output, and if we trust it blindly, like the questions we had before about the medical domain, dangerous in that sense. But dangerous as in the robots will take over and kill us all, that philosophically, that means people don't understand what intelligence is. To be dangerous, you have to be conscious of making a dangerous act, right? And machines will never be conscious and making a decision consciously to hurt someone because I felt like it. Consciousness, I don't see it in machines at all. These will always be deterministic automata. They will function according to the logic I program, and they will function according to input-output logic that we know and love in computer science. So they will never get to a point where they consciously, right, decided to go out of the logic that we programmed and do something funny. That is just science fiction.
So I guess okay, no more
We're
questions.
safe. We're safe.
Yeah, we're safe. So no more questions at this point. We'll have questions after you finish the presentation.
Okay, should I go on?
Yeah, please go ahead. Yes.
All right. So let me recall my thread of thinking. Okay. Because I also do continuation like ChatGPT.
Everybody's very eager to ask these questions, so you have to excuse us.
No, these were beautiful questions, not at all. Okay, so here's the idea that the idea that words get their meaning from their context is not new. This is old stuff. And like I said, over a century ago, Frege knew that, and Fred Sommers also, who I love his work on the tree of language, he calls it. And basically, it's also a Wittgenstein. The meaning is the meaning in how we use words. That's where their meaning is. So Fred Sommers used this technique to discover the ontology that seems to be implicit underneath language. And the way to do that is basically analyze how we use words in language, in common use, we call it ordinary spoken language. So that inspired me a lot. They had two good papers, one before I was born and one the year I was born. Okay, another one that I really value, he's a great computational linguist, Jerry Hobbs. He had a nice phrase at the end of his paper where people stop reading, basically, and that's really, to me, where the gist of the paper was. He said something brilliant. He said, if we can assume a theory of the word that is isomorphic to the way we talk about it, because he said there are two ways to model the word, like I said, top down, bottom up. Top down, it'll take us a century before we discover how the word functions, and we'd have to solve every problem in physics and biology. So that is hopeless. Another way, because a system that understands language properly has to have a model of the word, because that's what we use language for, to talk about the word. And he said one way to do this is the other way around, which is build a model that is isomorphic to how we talk about things, and then we will discover what they are, right? Which is, again, a bottom up. See how we talk about things, and from that, discover how language works. So again, brilliant idea. And yours truly said in 2006, one way to discover the meaning of words and the meaning of phrases is to discover them by reverse engineering language itself, because the best model of language is language. We want to understand how language works, reverse engineer it and see how it works, right? Okay, so where am I going with this? Okay, so the best thing, we know now that language cannot be approached top down because we have nothing to go by. It's a dark box, what happens inside. So, and large language models have proved that a bottom-up strategy is a viable strategy. How can we do this, but symbolically? Well, we've been doing something similar for a long time and we didn't know. If I have something, call it mask or X, plus 3, for that expression or for that sentence, in arithmetic, an expression is a sentence, an arithmetic sentence, if you want. For that expression to make sense, underline the word to make sense, 3 must be a number, right? I mean, this is called type inference, right? A language like Haskell, you don't define types, although they are strongly typed, but they do type inference. They infer the type. And if the type unification doesn't make sense in programming languages. If it doesn't make sense, it's a type error. So if you write a tuple plus 3, it will say, wait a minute, or a list plus 3. You're adding a list to a number. That doesn't make sense. Hey, in formal languages, we speak of common sense, right? So that's not completely new. Now let's go to language. If I said mask or X told me that she's tired, mask is not a table. I don't know if any of you have ever heard a table said she's tired. It's not a mountain. It's not a car, right? Mask is a person. People say, first of all, talk means we have a talking thing here, and that's people, right? So far, so good. Okay, so the idea of reverse engineering language is not about co-occurrence, what's around me. It's about the company I keep here is more than that. It's type unification. I'll get to that. But here are examples. Here's another one. If I say, try the X, try the mask, it's very tasty. Again, you can infer the type of, and usually what we do, this is important, what we do is we infer the most generic type, right? Like in the first example, mask plus 3, for that to make sense, mask must be a number. I didn't say it must be an integer or it must be it doesn't matter. So usually we infer the most generic type possible, right? So here, food, anything that's food can go in this slot and the sentence will make sense. Try some food, it's very tasty. So it's a type inference again. Or the mask took very long, the X took very long. Usually X is some sort of an event, right? The seminar took too long, the trip took too long, any kind of event type. Okay, so the idea is not new. Like I said, languages like Haskell or Miranda, or they do type inference because they're strongly typed, and before runtime, they have to make sure that all the typing is correct. Although you don't define types, they do type inference, we call it. And type inference is really reverse engineering and asking, what is the type that will make this thing make sense? Okay, so by reverse engineering bottom-up language, these masks can be discovered. And I'll show you more. Implicit in that inferencing mechanism bottom-up, a type hierarchy will be discovered. In other words, we will discover the ontology that is implicit underneath language. Okay, how we're doing on time? Okay, we can do a bottom-up corpus analysis to discover something like this. And I've done that before. This is old work, but I'm continuing with it. So we can discover that, hey, it looks like heavy is something that is applicable of, or it makes sense to say of things that are physical objects. Hungry only makes sense of X if X is a living thing. We don't say hungry street. Forget metaphor here. There's more complication here, but we can deal with them, but let's not complicate things now. If I said X is articulate, X is some kind of a human. If you like to think that animals can be articulate, we can generalize the type from human to animal. rational or irrational. Usually people make things, and the things that we make are artifacts, and so on. So we can discover these basic type constraints, right? This is just an explanation that I just went through. Now, implicit in these is this. Actually, when we discover these, so for example, take we can manufacture, people manufacture instruments, right? This is a subtype of we make artifacts. One way of making is manufacturing, and one type of artifacts are instruments. So if we discover these constraints, implicitly and indirectly, we're discovering the ontology that seems to be implicit underneath language. That's beautiful. We're not just discovering what goes with what, but we're also discovering the taxonomy of the types that we talk about in language. And if you do that at a scale, you might uncover, like archaeologists, the innate and apparently implicit and universal, by the way, I'll get to that shortly. It's a universal ontology. It's not German, it's not Greek, it's not Hindu, right? It's not Arabic. It's a universal cognitive ontology that's underneath all natural languages, and I'll try to convince you of that shortly. Here's where I'm going to try to convince you. There's a phenomena in that occupied linguists for a few decades. Basically, they called it a mystery or a puzzle. And okay, the puzzle is this: when we have more than one adjective, at least two, but even more, but let's make it simple. We tend to order the adjectives in a certain way, and we don't know why. Naturally, we find it more natural to say them this way, not this way. And even for a 5-year-old, remember, we don't stop at children. Like, let's take, we don't say, I bought a red, beautiful car. We say, I bought a beautiful red car. And when we have beautiful and red, we don't stop a 5-year-old and say, hey, remember, if you have beautiful and red, you put beautiful before red. We don't do that. It just comes out naturally this way. So it puzzled linguists for decades. Like, what the heck is going on, right? And so it's a problem that intrigued me because I was working on this bottom-up reverse engineering and discovering how language works. I said, if I'm going the right way, my system should explain what's happening, right? Otherwise, we have a problem. And I did explain what's happening. Actually, this paper won the Outstanding Conference Paper Award. And it turned out that this ontological structure, this strongly typed structure that we discover, is at work. And why this is interesting, because remember, this phenomena is universal in all languages. Now, in some languages, the order is in reverse, but semantically, conceptually, what's happening underneath is the same. You know, some languages, everything is the other way around. But conceptually, the same thing that I'm going to explain here is happening. Look at this mystery. That's not a mystery anymore. And it's related to strong typing and programming and computing and type checking and typecasting. It's all one big story. And that's what's beautiful about this. For a computer scientist, anyway. We know from type theory and from programming languages that casting down is undecidable, but generalizing, casting up, is okay. I mean, I can always generalize. I can always think of the car as an artifact. I can always think of the car as a physical object. And I can always think of the car as an entity. So I can keep going up. I can generalize as much as I want. But I'm not allowed to cast down. I cannot assume that my artifact is a car. Why? Your artifact could be a couch, a sofa, right? So we know in logic and type theory and programming languages and computation, casting up is fine. I can always generalize, but I cannot go from one type to any of its subtypes. I cannot make this assumption. That's undecidable. And that's what's at work. Imagine in this so-called mystery. When I say a beautiful red car is better than red, beautiful car, because once I said red car, once I said beautiful car, I made it an entity, because beautiful can be said of any entity, whether abstract or physical or anything. I can say beautiful poem, beautiful idea. So beautiful is way up. Once I commit myself to beautiful at that level, I cannot now bring it down and say it's red. But if I said red, all I committed myself to is a physical object. I can still raise it up and look at it as an entity. That's why this is more natural than this. And mystery no more. Okay? But the interesting thing about this is, here's type theory and casting rules that we use in programming languages are at work in a language phenomena. Same machinery apparently is at work, same logic, which I found it amazing. Okay. And the system I'm developing started to solve bigger problems. Imagine you're in a diner or a restaurant, or and you hear this: "Hey, Sarah, the loud omelet wants another coffee." I don't know if you heard it, but I can give other examples, doesn't matter. But we hear stuff like this, right? And what we really mean, unless you know omelet, some omelet that can be loud and that has wants and likes coffee, what really we mean by this is, "Hey, Sarah, the loud person eating the omelet wants another coffee." And we have these examples. These are not exotic examples. This is the norm. That's how we speak. We say the New York Times endorsed Biden. The New York Times, whether it's a company or the physical newspaper, they don't endorse. It's the editors at the New York Times. So this indirect reference, it's called metonymy in language. We do all the time. But for a machine, it's going to look at this and say loud omelet, and the omelet wants coffee. Okay, real deep understanding requires what? We have an expectation. Remember those type constraints I said we would like to discover? We have an expectation that expect a person as the agent, and the object of our wanting can be anything, let's say. But what we found is I have a want by a food object and it wants some beverage. Now the beverage and the thing unifies, that's fine. A beverage is a thing, so okay. If you can want anything, you can definitely want a beverage. So that's fine. That part works fine. Type unifies, type unification wise, we're okay. Now we have a person and food. And if we go up the tree, they don't have the same parents, so they don't unify. That means there's something implicit here, hidden. And what's hidden is that blue thing. We want to uncover it. We want to uncover some hidden information we didn't say, and we can with this type unification. We go up and we find that the most salient relationship between people and food is the eat relationship. So it's the person eating the omelet that wants another coffee. Now, this is easier said than done, but this is really complicated stuff. And it's all a function of discovering these type constraints bottom up from analyzing language itself. Okay, so I'm gonna get a little bit into my proposal, which is use what we learned from large language models, ChatGPT, like when their achievement. The first thing, how much time, Marcel, do I have? 10 minutes?
I think, yeah, 10 minutes would be good.
Okay, I'll try to go here a little bit faster. Okay, so the idea that I started developed, actually, I just published a paper on that, is we want to go into a language agnostic representation. By the way, if we don't solve the language problem in a language agnostic way, then we haven't done anything. Because the way we process language, like the examples of the adjectives I went through, apparently underneath we have one language. We have the language of thought. Jerry Fodor calls it mentalese as opposed to Japanese or Chinese or whatever. And the idea is, how do we go there? Now, if you have something like Sarah is articulate, okay, in English we say articulate, in some other language we say something else, and sometimes a word here is 2 or 3 words in another language. But really underneath, what are we saying? We're saying there is an object, a person, in this case, Sarah, and we have a property called articulation, and we have some relation between them. So really underneath, all we have, so everything is a thing, everything is an entity, and we have some relations between them. This is going back to the old ER model and the entity relationship diagrams. Everything underneath is things, and we're talking about these things in a certain way, right? So here we're really what we're saying, the thought behind this is there's an object who's a person, there's some abstract object called articulation, which is an entity like any physical object, and we have a relationship between them. Specifically, Sarah has that property. Oops, Sarah ran for a mile. Again, we have a running activity as an entity. And Sarah, a person, and we have a relationship between them. Specifically, Sarah is the agent of that activity, and so on. Let me show you. Okay, is the agent of or has property of, these are the primitive relations, and there's a way to discover them. I don't want to go to the two details here, but essentially, if you have examples like X is Y. Now, there are many possibilities. Well, not many. Actually, there are 4. Type 1 and type 2 could be the same. 3, actually. Type 1 and type 2 could be different. No, 2 only. So if I have same type, but there's sometimes the type could be more generic or more specific, and here we can go into. But basically, I have X is Y. If they're of the same type, here is equality. So my primitive operation is the last one, G. An example is JFK is John Fitzgerald Kennedy, or AUB is the American University. Basically, it's an equality relation or a synonymous relationship. And I have, obviously, Liz is famous. Now I'm saying some object is an adjective. What? Well, what I really mean is I have 2 objects, fame and a person, and there's a relationship between them. So this is saying Liz has the property fame. John is aging now, is going through some process, the process of aging, and aging now is an entity. It's a process, and so on. Okay, that allows me to discover what we call language agnostic primitive relations. Why do I call them language agnostic? Because in every language, forget the external grammar and specific details of that language, underneath, as a cognitive primitive, all humans understand that there are events and there are agents and objects of that events. There are things that have properties. So these are things that are culture and location and time and language agnostic. These are primitive cognitive relations that all humans understand and can conceptualize. Okay, so underneath, what I'm saying is this is how we represent thoughts. So the small knowledge graph on the left-hand side is saying John made a brilliant acquisition. Now I can read this. The acquisition that John made was brilliant. I can read it in so many ways. That's besides the point. That's the external language. But underneath, all I have are entities, the blue rectangles, and I have primitive relations, something like the agent of, the object of, the theme has property. That's all we have. Of course, the challenge is to get there. On that subject, I just had a paper accepted actually a week ago. to a very good conference. It's one of the top on computational semantics. And the idea is this, I was suggesting how, because knowledge graphs now have this alignment problem, like your knowledge graph or mine, and people use different language. And I'm saying, no matter how many alignment techniques you make, this will always fail unless you have a language agnostic primitive representation. Okay, I think we're almost there. So going forward, what am I suggesting? To summarize, these bottom-up reverse engineering of language at scale, a la ChatGPT, have taught us a lot, that this is the right way to uncover what's underneath language. But we need to do it in such a way that we have explainable, not unpredictable, statistical, accidental correlations. We need to do it symbolically or think of it as conceptually. And as a net result, we will not have just systems that know how to use language, but we would have discovered how really language works and maybe how the language of thought, the internal language works. So we will be doing real investigation. So the dimensions we want to learn are these things. What are all the things that a book can be an agent of? A book can be the agent of convincing, the agent of influencing something, the agent of change, and so on. What are all the things that can be properties of books, and so on? This is what we want to learn. These are the dimensions we want to learn conceptually, not 300 points in multidimensional space because of co-occurrence or correlation. These are the things we want to learn bottom up conceptually. And thank you.
Thank you. Thank you so much. Thank you for this.